Now, in section 3.4, we will discuss the multipole expansion, and in this expansion, we will calculate the approximate potential at large distances. And we will solve example 3.10, which will guide us toward this expansion. There is a question that when we are having a charge distribution, whether it's a point charge distribution or any other distribution, and we suppose that charge Q is there, then what will happen when we go far away from this charge distribution? And we know from our previous knowledge that V of R is equal to 1 over 4 pi epsilon naught Q by R. So what will happen at large distances? At large distances, we say that as R goes to infinity, then V of R goes to 0. This happens at large distances. Now, the question is that what will happen when Q will be 0? Then of course the answer is that the potential will also be approximately 0 even if we are at large distances. But the question is that how quickly this will go to 0? Then this depends on the geometry. This thing we derived for basically a monopole charge distribution, like a single point of charge distribution, and the potential comes out to be Q over R, means it will come out to be 1 over R. What if we consider the charge distribution to be in the form of a dipole, like 1 plus and 1 minus? Then we will come to know after this expansion, or which we call the multipole expansion, because here it's a monopole, single pole. Here it's a double pole, means it's a dipole, and then a quadrupole, then we are having 2 dipoles together, and then 4 dipoles together, we are having octupole. Basically, this depends on the charge distribution, that what kind of charge distribution we are having, due to which we will determine this potential. So if we are having a monopole, then it is 1 over R, the potential will drop is 1 over R, means it will drop slowly. But if we are having a dipole, then it will fall comparatively quicker than that one, because it is falling is 1 over R square. Similarly, for a quadruple, it will fall is 1 over R4 and 1 over R3, and for octupole it will fall is 1 over R4. So this we are having, when 2 poles there, we are having R square. When 2 dipoles are there, we are having R cube. When 4 dipoles are there, we are having R4. And similarly, we can extend it to when there are 6 dipoles, then it will fall is 1 over R5 and so on. So this will continue. So it means that at long distances, the potential will fall to 0 for all the geometries, but which one will go quicker? That is the thing that we will find out in the multipole expansion. So starting with example 3.10, and let me read the statement of example 3.10. You will be also seeing it over here. So example 3.1 says, a physical electric dipole consists of 2 equal and opposite charges plus minus q separated by a distance d. Find the approximate potential at points far from the dipole. So we are basically now considering for the monopole we have already done, and it is 1 over r, and as we are at large distances then it will fall to 0. So what about a dipole? And then let me first draw the geometry of this thing. So the geometry is that we are having a dipole, and for mathematical ease I am considering its geometry like this, that here this is a dipole that I am considering, and we are having one charge here while the other charge here, and this one is plus q and this one minus q, and this is the central point. The distance between the two is distance d, between the two charges it's distance d. And now I consider the observation point slightly, you can say, just above this line in order to make my mathematics easier and in order to see different things. If I just consider exactly over here the observation point, then I will have no angle involvement, and this will cause my calculation to be not more conclusive. So I will have to consider the observation point slightly above this point in order to introduce a tilt, and that tilt will basically introduce an angle. This is our observation point P, and I will connect this with this one. So it's here, and then this distance usually we consider is this makes an angle theta with this, and from the any point I consider this distance is r, and here from the source to the observation point we always consider the distance in tilted r is r plus due to the positive charge, and here I will consider this is r minus, and this makes our geometry. And now I can write the potential for this geometry. The lines are a bit tilted, means my geometry drawing is not that perfect. Okay, so we have the potential. Now I know that the potential due to plus q will be at a point P, the observation point. It will be this one q over tilted r plus, and from this it will be tilted r minus. So I can write the two potential together. The plus will have a positive potential and the minus will have a negative potential. So let's write this one. V of r, V at point r will be equal to 1 over 4 pi epsilon naught, or let me take this thing, the q is common as well. So q over 4 pi epsilon naught, and here I will have 1 over r plus, and then the next potential is minus, so it will be 1 over r minus. This is basically the potential that we are having of this dipole. Now I see here that what about here, if I write r plus, and this is squared, then I can see from the geometry that what this thing is equal to. This is a triangle. Okay, this is a triangle, and if it's a right angle triangle, then there will be no angle involvement, and I can exactly write from the Pythagoras theorem that this is the base, which is d over 2. This base is basically d over 2. So d over 2 square base square and the perpendicular square will be equal to the hypotenuse square. So this is the Pythagoras theorem or the distance formula that we have, and as we are having a tilt introduced here, so cos theta will be involved here. So I can write that this thing is equal to r square plus d over 2 whole square, and this is minus, and is the law of cosine is saying this thing, this will be 2 times r and then d over 2 and cos of the angle. So this is the law of cosine that we know already, that this square, this tilted r square is equal to this r square plus d over 2 square and minus 2 times r, this is this r, and then d over 2 in cos of the angle. So these two are gone and we are having minus rd cos of theta. Now I can see here another thing. What if I consider the r minus? Then for the r minus, this will be, when this will become r minus, so it will be r square and again d by 2 square, so r square plus d by 2 square, and then you see here that this is the angle is in reverse, or you can say that when angle is like this one, then it will be phi minus theta. So this angle means theta will be separated, means subtracted from here, and it will become phi minus theta. So I can write this thing is, this will be equal to minus, this is plus plus, and this will become plus here. So this thing is clear now, and now I can write that this can be simplified to, if I take r square is common, then what I will have? I will have the, for this I will have 1 and then plus, this will be equal to d square over 4 in r square. So d square over 4 r square, and then this will be minus and plus, so it will be rd and then 1 r here, r square, so it will be d over r and cos of the angle. And here we are having the relation like this, which I can further write is in terms of r, I will write this r square and then 1 minus plus d over r and cos of the angle plus d square over 4r squared. So I have basically written this thing is 1 over r and 1 over r squared. Now as we are interested in this thing, that what will happen when this r is very greater, this r is very greater than d, means compared to the distance between the dipole, between the two polarities plus and minus, if this distance is very small compared to this one, when we are very far from this charge distribution, then what will happen? We can see clearly here that this term will go to 0, because This is r square. R square will be further greater than this one. So this term contribution will be negligible, and I can write that r square plus minus is equal to r square, and this will be approximately. This will be approximately equal to this, and this is 1 minus plus d over r and cos of the angle